So hello everyone, once again, and the topic of my presentation is how is AI changing our world? And first of all, I would like to pose a question. So please raise your hand if you are optimistic towards future with AI and that the net positive effect of AI will be positive. Great. And please raise your hand if you're a little bit more on the pessimistic side and you think that the overall effect will be net negative with AI. Well, with every new technology, there's always room for pessimism and optimism. There are strong believers and very cautious skeptics. And speaking of skeptics, you have probably heard that this open letter circled around which warned us of existential risks and demanded not just pausing, but immediately stopping all development of AI across industries. And if you read the letter, and if I read the letter, I understand that even I should pause my development in my lab at TalTech. So what to gain from that insight? Even big prominent names, contacts signed that letter and also warned us about these risks. However, there's a room for skepticism when we read these extreme opinions, like immediately shut down existential risks, because some of the people who signed the letter, they were also stocking up on GPUs. And of course, there are sincerely people that are concerned, and there should be, but with these extreme opinions, we should take them with a grain of salt, as maybe the other agenda could be to halt the competition, to catch up. We don't know. It's quite interesting to look into the history and see what other waves of technological breakthroughs what effect did they have. And there's a very interesting blog called Pessimist Archive. And you can look up the media headlines from 100 years ago. So combustion engines, right? Printing press. So what happened then? What were the emotions? And the narrative was quite similar. So the robots will take over, we will lose, all of us will lose our jobs, and etc., etc. So there's a saying that history never repeats itself, but it often rhymes. So there's very interesting to look at the patterns. And the same is with AI. AI is not a new concept. This is a headline from 1950s where the first sparks of AI were present. And the most maybe popular one of the most popular, how would you say, critics or skeptics was cybernetic Dr. Norbert Wiener, who warned us that if we will not stop it immediately, something bad will happen to humanity. And he was talking about, I believe there was first self-learning checkers programs, and there were already quite a lot of extreme opinions around it. So speaking of history, I will not bore you with a history lesson, but I think that it's very important to highlight some of the milestones that brought us here where we are today. And we are today with these fantastic tools, ChatGPT, Gemini, Claude, Llama, and other generative AI tools that, well, let's take a quick survey. Who uses one of these tools? Also maybe image generation tools like Midjourney or something like that. Okay, not everyone. That's interesting to see. So ChatGPT was down a couple of days ago, so probably some of you switched to maybe Gemini and discovered that, oh, maybe I can do something with Gemini as well. So how did we get here, right? Let's just go through some couple of milestones. And as you can see, AI is not a new concept. It has been around for 70 years with its ups and downs. There were some AI winters where no one was talking about AI. There were some hypes where everyone was talking about AI, and now we're again at the hype wave. So what was the precondition to that? Well, first of all, in 2010s, the convergence of GPUs, compute, right? Big data, and magical mathematical concept of neural networks, which I will briefly introduce. I will not try to bore you with too much of the details, but I would like to show you a bit under the hood what happens inside of these neural networks, or deep learning in other words. So the the explosion of deep learning algorithms was born, and image recognition, computer vision changed. So another breakthrough was in the purple color there, and it was called discovery of transformers, or presentation of transformers. Who have heard of the word transformers in the context of AI? Why is it important? So it was a paper that Google research scientists published in 2017. And it's important because we're using transformers on a daily basis. Do you know what GPT stands for? Generative Pre-trained Transformers. And transformers is an architecture of neural networks that Google researchers presented. And today's innovation stands on the shoulders of, well, not just Google scientists, but previous scientists who discovered convolutional neural networks, transformer neural networks, and of course the convergence of other factors played a huge role. So let's remember that. And it's actually a very good example, the transformers example, that how do we use AI on a daily basis, but we're now not even acknowledging that. For example, transformers revolutionized the field of natural language processing. It allowed us to, well, in simple terms, read the sentence as a whole, not just word by word, and it introduced the notion of attention or importance to the word itself, so the algorithms understood the importance of each word. Doesn't matter where in the sequence, in the sentence it was. For example, before the discovery of transformers, the Google search looked something like this. So we want to search from Brazil traveler to USA. We need a visa, and it gives us some output that includes all of these words, right? But after the introduction of transformers, it understood that the word to has a meaning, and it has kind of direction. So Brazil to US, and it gives much more sophisticated outputs. So we didn't notice that. Did you notice when did the Google search had the summary section? It was also after the introduction of transformers where the algorithms become much more sophisticated. So the development was there, but the boom is right now because we can use them. We can interact with them, and it seems like magic sometimes. And I would like to cover that a bit. Why is it seems like magic? Does it seem like magic? Okay, so I bored you with terminology. Let's just pack the things in the right sectors, because we use a lot of words like AI, generative AI. So what does it mean? So how do they relate to each other, right? So just briefly, artificial intelligence is basically a discipline that teaches computers to mimic human behavior. It doesn't have to be machine learning that we use, for example, that I use. So it can be maybe some robotics-related task, or some sensors that mimic human vision or something like that. So not everything that is artificial intelligence is machine learning. However, machine learning is quite a large chunk of the artificial intelligence nowadays, because it's an absolutely magnificent, discipline that extracts gains insights from the data without being explicitly programmed. And I will explain that with in detail, not in detail, but more clearly with my own example, how I use machine learning on a daily basis. So, and again, deep learning and generative AI are subsets, because generative AI uses neural networks, right? Transformers. So it's a subset of deep learning. So when we say ChatGPT is an AI, yes, it is, but it's a generative AI, right? And it's not just equal sign between them. And deep learning, well, whenever we use neural networks, we have to stack them. They're deep. They're not shallow algorithms, so we use the term deep learning. Now we're on the same page. So we know about the history, we know about terminology, so let's talk about a couple of examples how AI could benefit society and why we should be excited about AI. So this is an excellent example of what it can do, because it's a magnificent algorithm that can analyze a large amount of data, right? Where can we use it? 3D protein structures. I have no idea what it is, but I have read, so I will pass that information to you. But if you're a microbiologist, I apologize in advance. So as I understand, 3D protein structures are the building blocks of our body. And they are common reasons why we develop some diseases. So cancer, Alzheimer's disease is an actually misfolding of some of the 3D protein structures. So if we know them, if we study them, it will probably help us discover treatments, prevent some diseases, and find yes, different cures, speed up drug discovery, etc. So, to give you some context, before AlphaFold, we knew about 17%, we, researchers, I didn't know anything about that, but we 17% of all possible 3D protein structures. And every new discovery was big deal. It was a big deal. It was like a PhD thesis or a Nature scientific article, so it was a big deal. We discovered one protein structure, it validated it, yes. Now, we know 98.7% because of artificial intelligence. And actually a couple of weeks or a month ago, the Google team and DeepMind team released an AlphaFold 3, which is a latest version. And I believe that it's even more accurate, and some even say that it's worthy of a Nobel Prize in medicine, because it has an extraordinary impact on understanding diseases and curing diseases. Next one. NVIDIA. NVIDIA is surpassing Apple and it's like price, so it's a big company, right? And they have a lot of resources, so let's hope they use it for the good. And one of the projects is to digitalize our planet Earth. And they have a digital twin model. You know the concept of digital twin. We know the different parameters, and we just synthesize them in a digital model. And they have very high accuracy and very high resolution of our climate. Climate is important issue. We have to predict some disasters through climate change, and this model allows it with a very high precision. And knowing NVIDIA, knowing the resource they have, I believe that it could also become something that will help us greatly. GPT-4o. O stands for Omni, right? So it's multimodal now. So it's not just text. It can understand audio. It can understand it has some computer vision capabilities, and there's a lot of use cases for that. But this one is close to my heart. My parents are teachers, and I have been teaching in university and high school, so this is great. And there are actually studies that say that if every student had a personal tutor beside him, who is patient, who doesn't mind if a student asks stupid questions for the 8th time, doesn't understand you. So the achievement of students will skyrocket. Some studies suggest 2 sigma rules, like 2 standard deviation much. Or one study said that 80% would be the increase in achievement if every student had personal tutor right beside him, right? But it's not human. We don't have resources to cover that. However, artificial intelligence could help. And this is exactly the same example that I'm describing. It just coaches and directs the student through the geometry or whatever exercise it was. So it is patient, it is well, smart enough to teach, right? And I think it's a wonderful use case. And I hope that the education system will definitely look into that. Last one, I promise. This is also a use case of ChatGPT 4o. They're partnering with visually impaired studies, And one of the use cases is helping visually impaired people to manipulate our world, to feel our world in much more convenient way. So for example, this was one use case that it could say, help you to hail a taxi at an exact right moment. So it will have the computer vision capability and say, raise your hand now. So great. I think it will make their lives better. So these examples are from big, huge tech giants, right? They have billions in resources, so that is great if they're using them in the right direction and right to benefit. However, you don't have to have billions to leverage AI to do something, to do your task, or to make something positive. I would like to share some of the projects that we do at TalTech, more specifically Department of Software Science. And I already mentioned that I work with human motor function analysis. It means that we analyze fine motor skills like handwriting, gross motor skills like gait, and the application is in healthcare so far. Parkinson's disease is the first one. So how does it work before the digital era? How does it usually work? It's even a process now. You go to the neurologist office. You will be asked to fill out some drawing tests with pen and paper, right? And the neurologist will take a look at your drawings and say that you probably don't have Parkinson's disease, or you might do some additional tests. So we use tablet PCs to automate, or kind of optimize or streamline the paper and pen process. And of course, we can calculate, or we can extract digital signals like coordinates, timestamps, the orientation of the pen, and pressure that is applied on the tablet. So much more, how do you say, information dense process. Why do we do that? Why do we need machines to help with that process? So there's an example. So this is a spiral drawn by one of the study's subject. And if you know Parkinson's disease, the symptoms are tremor, shakiness, muscles are rigid, and it shows in the handwriting, right? It can become like shaky and not so smooth. So what do you think, who drew this spiral? Is it a healthy person or the Parkinson's patient? Parkinson's. So this is healthy and this is Parkinson's. I can't draw that good on the tablet PC. This is very smooth. So as you can see, you're going to have 8 years of experience to make some differences, or maybe look at the beginning of the spiral and there are something that doctors understand. Of course, you can do more tests. Maybe this test was just not enough, of course. But it kind of opens up a gate that we should look deeper. It's not just a visual analysis. Let's understand what happens inside. And now I would like to briefly explain what is the difference between machine learning and traditional programming. But first, machines do not understand images, text, videos. They understand what? Numbers. Everything has to be encoded to numbers. So, for example, I mentioned that we collect digital signals like coordinates and timestamps, pressure, etc. So, what can we do with these signals? We have these spirals. Yes, we can use them as images and encode them as pixels, but let's try something different here. Let's take a look at the kinematics of the handwriting. So we can calculate, we have the distance and the time, physics, we can calculate velocity. If we have the change of rate of velocity to time, we can calculate acceleration, and we can go further. Just a quick physics lecture. Did you know that they have really fun names if you go further with the derivatives, like velocity, acceleration, The next one is jerk. And the next ones, we also calculated next ones. And this is from the physics materials. I didn't make them up. Are snap, crackle, and pop. So they're very fun. And they're used in cosmology as well. So it's not just imaginary numbers. And they became very sensitive in detecting Parkinson's disease for machine learning algorithm. And it actually makes sense. We can interpret that or can kind of feel that maybe there's some micro changes in the handwriting that we can't see, but they are there, and maybe machine will spot them and the human will not. So this is our hypothesis, and this model that we trained on the kinematic features were quite accurate, very accurate actually, but we have of course validated and tested more and more. So this is the overall framework. We collect the data, we engineer the features, we find suitable machine learning algorithms, and they are not usually the bottleneck. I will talk about bottlenecks. There are a lot of machine learning algorithms which are best of the best, but they need data and features and, well, a lot of this that comes before is important. And the prediction, of course. Another way to feed the data into the algorithms, and we have different kind. We can pick the algorithm, say, I have the data for you. Let me see, how can I encode the data? So I mentioned images, and images have pixel values, right? And you can put in 2D images, but we have algorithms that learn from 3D images. Let's use them. Because we have kinematics, right? And why just throw them in the garbage and just use images? Let's encode kinematics into our image. So we used the pressure parameter to define the thickness of the spiral, the volume. And we used velocity to note the color. Like whenever it's yellow, it's higher, and etc. So we fed these enhanced images to the machine in the hope that it will understand more in depth what is happening and spot these patterns. So this is the main difference between traditional programming and machine learning. With traditional programming, we had to encode the rules as well. So listen, whenever you see the yellow line, which the threshold exceeds this and that, then it's a healthy person, right? Or the thickness of the spiral. In here we have voxels. 3D are voxels and 2D are pixels. So wherever the voxel thickness, whatever is this, then say it's a Parkinson's patient. With machine learning, we don't encode any rules. It learns it by himself or herself. So what do I mean by that? We just show a lot of examples. So these are the healthy spirals and these are the Parkinson spirals, and you learn the rules. How it does it, we will briefly touch upon it, but basically it's just mathematical optimization and function approximation between these classes. So between the input and the output. So it doesn't, you don't need to input the rules, and you just hope that it will approximate the function for you. This is the function. So I just simplified it to 2D. Pixel values are the squares, whatever, just a random number is written here. So the resolution is 28 by 28, but it's of course just for to simplify things. And again, the first layer is like the number of all the pixels stacked, and it's not how it's usually done. We use convolution and different methodologies just to simplify how does it work in brief terms. So, so for example, we want to use neural networks to classify this image and say and understand whether or not it's a binary class, or it's a 0 for healthy or 1 for Parkinson's patient. So what happens inside? Every connection, and these layers are for us to decide. How many layers do you want? How many neurons do you want? It's an engineer's job to do, or you will use already out-of-the-box algorithm. So let's just forget about that. But I just want to briefly explain the concept of neural networks. How does it learn? So first of all, you will have, for every connection, you will have a parameter, because functions have coefficients, right? We have a function, we have a coefficient. And these coefficients determine the output. right? So at the beginning, you have random coefficients, trash. It doesn't know anything. Doesn't know anything. So these coefficients, and you can see how many there are already with this small neural network, which has, well, I don't know, 40,000 maybe parameters, right? And it already looks like a black box, because it's very hard to say which coefficient determined the disease. So, and this is very small. And the first prediction is probably trash. And you can see that, well, it's 0, but it has to be 1. And what do we do by during training? We want to bring prediction and the ground truth closer, right? It's not just difference between them. It might be, but it's usually some mean squared error or cross entropy loss, whatever it is. But the basic intuition is we want to bring them closer. So the first prediction is trash. We say that no, think again. It will adjust the parameters based on some optimization algorithms, whatever. It's all math. However, the basic intuition is it goes back, tries with the new parameters, and picks a new prediction and says, is it correct? And if it's correct, then it will save. And at the end, you will save the weights, and this will be your model with the correct coefficients. So we want to minimize the difference between the prediction and ground truth, and we do that by adjusting the weights. And whenever you're using open source models or open weights models, Llama, for example, right? It's not completely open source because they don't share the data that they trained on, but they share what? They share these coefficients. So you don't have to retrain your model. Okay. So this example was of a predictive AI. It's a predictive AI model that outputs label. Just briefly go through that. We have a generative AI that does not predict a label or a class. It predicts not predicts, but outputs new content. It does have some predictive AI models inside that predict the next word by a probability distribution, but at the end it generates new content. And to just again go through what is AI, Gen AI, and what is not. So Gen AI is not, when it's output, it's just a number. It's discrete, means that it's just it's not continuous, and it's class or probability. But whenever we receive some text or image and audio, it's generative AI. So we talked about use cases and benefits of AI. Let's balance it out with a couple of challenges that we have with building these systems. I don't have much time. I don't spend much time thinking about sci-fi scenarios and how it will ruin us. But I do spend time thinking about what are the immediate challenges and how can we mitigate them. First, they're very data-hungry algorithms. As we mentioned, they learn from data. They don't need the rules. Don't tell them the functions. Just give them the data, and of course in the correct form, and pick a right algorithm. But it's very hard to obtain quality data with the right labels and everything in the right spot. For example, if the language model is trained on Reddit conversation, on Reddit data, will it give you adequate responses every time? No. So whatever it's trained on, it will learn from that. So it's quite a big issue, especially in healthcare. Because, as you understood, we have to have labels with the data. In supervised learning, there are other types of machine learning, but in this case, to deep learning, we had to have the labels as well. We didn't know which was Parkinson's patient and which was the healthy person. If I want to classify trucks and cars, I can do it. I know which one is truck, which is car, and I can just take 8 hours of my day and just go through them, right? But with health data, I don't have the qualifications for that. So it's very expensive to obtain health data. We have to ask doctors to label it, and they don't have time, or it's very expensive. So this is a bottleneck that I have in my work, how to obtain quality data, how to label it, etc. The second one is low interpretability. You saw the messy neural network, right? And it was only 40,000 something connections, or the parameters. ChatGPT or GPT-4 has 1.8 trillion of these parameters. Like it's not a black box per se. You can definitely go through and find a way, but it's in practice it's quite hard to say why did it answer that or that. And I have an example from my work as well. I would like to share it with you. So on the top of building a machine learning model, we try to add explainability layers. So we want to go inside and highlight the parts of the image that the machine learning model found informative, right? And this model, if you can see, predicted out of 10 images, it predicted 9 correctly. So quite good result. And you can say that it's a very accurate model, and you can stop there and ship it, right? Take it. It's a very accurate model. It's performed one was outlier, so take it. However, if we build this explainability layer on top and look inside, why did it think that it was a healthy person and this was a Parkinson's patient? For the healthy examples, it looks outside of the spiral. It highlights background information. In other words, it hallucinates something in the background. So perhaps it's not very useful because it doesn't understand the task. It just understands the images that were brought to it. So if the data set will change, it will perform poorly. So we have to go deeper. We have another model. The explainability of this model is much better. It doesn't concentrate on the background at all. It goes inside the spiral, and you can see even consistencies among the classes. So for the healthy people, it concentrates on the beginning, right? And for Parkinson's patients, it's more concentrated in the center. And it actually aligns with the visualizations or analysis of the neurologists. They also say that for Parkinson's patients, it's very hard to stop. It's they tend to go until the obstacle and then change the direction. So perhaps it's also something that happening in the end, the acceleration or something is getting different or is different. And the beginning of the healthy person is also something that we could interpret. So you understand that there's the two models, they're both very accurate, but the interpretability is it's different. So it's very important to interpret these models, however, it's not very easy. Bias. Training data again. So the diversity of our training data, the diversity of our algorithms and the ones that are building it. So algorithmic and training bias. We'll try to illustrate that with an example. So, for example, we are annotators, right? We are given a million images, and we need to annotate that. We're humans, we're pretty good at that task. What is in the picture? How would you annotate this image? Watermelon, correct. Watermelon slices, whatever, juicy watermelon, whatever is necessary, right? What about this one? Weird. Yes, it's very weird. I haven't seen that. Well, there are some yellow watermelons, right? There are some yellow. And well, in this case, we have to specify the color, and it's not just watermelon. It's a weird watermelon for us because we are not. This is not something new for us. And the same goes, for example, with the description of a bride in Europe. White dress, bouquet, right? The whale. In Asia, oh, that's the different picture. They don't see the bride, or Asia is a very broad category, but you understand, right? In Indonesia or something. So we need to have diverse cultural and different classes represented in our data set. So in here, important thing to note is that it's quite dangerous to consolidate all our information diet to the US East Coast, so the East Coast and West Coast, whatever. So they will just control all of our information in terms of what they use for training, and do they have the data from across the world and different examples, or the bias is something that we should be worried about. And the last one is uncertainty, and it's actually a concept that is not just strictly defined. It just says that machine learning models and deep learning models are uncertain, and it's actually nothing. There is something we can do, but not to some extent, right? Because they need to be a bit creative. They have to generate sometimes something that wasn't there, so they can hallucinate sometimes, and it's a bit dangerous, for example, when we talk about autonomous vehicles. So if the data that we trained on didn't include the stop sign or the cliff somewhere which was now there, it will be dangerous because they're trained on the specific data, and for deep learning algorithms it's very hard to generalize outside the training data. So there's some uncertainties that we should be worried about. Hallucinations, just to go through the ones that we are most familiar with because we're using on a daily basis these LLMs, large language models. So what are the hallucinations? So there are generated outputs that sound very plausible but are factually incorrect. But they sound very plausible. And this is actually, so I'm not afraid of big mistakes like put glue on the pizza, but what were the examples? This is, you clearly understand that this is a mistake, right? But how do you fact check plausible outputs? So you have to fact check LLMs. And well, the question is when and every time, and it's very time consuming. Well, not every time. And whenever you are dealing with high stakes situation, you always have to fact check. You have to fact check humans, you have to fact check Google. Like it's common that you fact check things. So don't with the reference to autonomous vehicles, we can't sleep behind the wheel. So we have to have some control, right? But the help is definitely there. And actually, you can ask, or you can fact check inside ChatGPT and say, where did you get this information? Or is it really correct? Or please describe your work. Show your work, please. And sometimes it even corrects itself. So yes, the hallucinations can happen. There are mitigation tools. RAG, for example, retrieval augmented generation. So there are tools, however, at some extent, they are creative creatures and they will generalize. It's hard to generalize for them outside the training data, so they may come up with something that wasn't there. Sorry? Yes, so one of the mitigation tools is fine-tuning, and I will bring an example from the medical domain. So Google has a language model, well, it has different names, they're changing the names all the time, but it was called Palm. It was a very good language model, however, it didn't perform well in every task, right? So there were generalized text. And if we want to minimize the amounts of errors and hallucinations, and we want to teach these language models specific topics, we can fine-tune them on the separate data set. And that's what they did with this MedPalm. So they used the foundational models of Palm, and they fine-tuned it on medical questions and answers. This is an old slide. You can see 2022. I have the new one as well. It passed US medical license exam. GPT-4, which wasn't fine-tuned, which was trained on all possible internet data and databases, surpassed it without fine-tuning. Well, the new studies show that new MedPalm model is slightly better. However, I haven't updated the GPT-4.0 results. But what I'm trying to say, that you can use foundational models to fine-tune them on your specific tasks. For example, in this case, they used questions and answers from USMLE, which is US Medical License Exam, and trained the language model that already understands the text. It has a large foundational knowledge, and it trained the model. And the validation of that model was done by by doctors, and it wasn't just binary, that correct or wrong. It was also a scoring mechanism among these categories, like what is the likelihood of harm, was there bias present, how the literature is a consensus in scientific literature, yes. So correct reasoning and other factors. So it became much more deeper than just wrong or right? And maybe in the future we can trust these algorithms to provide some kind of first screening or give us direction to where to approach. And with health, even without artificial intelligence, you should get several opinions, right, before you stab yourself or something. So this is one of the example of the question. And I just wanted to highlight that if you don't know the answer, I don't know the answer. I know because I looked it up, but I don't know it by profession. So when do we trust these LLMs, right? So this is the question, and it depends on your task. It depends on your high stakes, or how high are the stakes. So you have to fact check. You have to be awake behind the wheel, but they're definitely very good friends, because this is the correct answer. So sometimes it hallucinates, sometimes, well, most of the time it gives us the right direction, and it is a helpful tool. So in conclusion, I think that we all here are try to be more in the center, right? So we're not panicking about, oh my God, it will kill us, the robots will rise, and then this and that, but we're also not in denial, like, oh, I don't need this stuff, it's some kind of hype, it will go away. So I think with every new breakthroughs, we should learn. We should try them, right? See how it will benefit my life, but not go overly fanatic and not be in a complete denial. So I hope that this presentation provided some valuable input and got you a bit more excited with AI. And thank you for the attention, and good luck with AI. I think so.
Yes, we do have time for questions, and if you don't have questions, we have QA, which is called question assurance. We'll just stick up a microphone at a random person, and you have to ask a question. So be ready, or have questions.
Thank you so much for your talk. It was very exciting, and I love your optimism in this area. I think the humanity will survive, of course, but there are questions like regulations. For example, when X-ray was a thing, there were tools like pedoscopes, where kids put their shoes in, their feet in these things, so they radiate the kids' feet. So to feed the shoes, only to feed the shoes. And this thing was killing kids until the regulation was in place. Mm-hmm. So how do you think, what kind of regulation can stop propaganda, disinformation, deep fakes, and all this stuff?
Yeah, a very good question. And regulation is something that I'm very interested in, but I'm not on that side at all. I feel the bottleneck that comes with regulation in terms of data privacy. I know it's important. However, I'll give you an example. We use cerebral palsy patients' body points, right, on the body. We don't need the face, we don't need the name, we don't need anything. We just need these body parts, and we can definitely map the process for rehabilitation with AI. However, to gain that data, we need from parents, from hospitals, we need a lot of paperwork. And to gain 10 videos, I got 10 videos. It took 2 months. This is how can we innovate in this kind of climate? Well, I try. but of course, I know the EU Act is dealing with these kind of high-risk situations, and they include medical diagnostics and face recognitions, which can definitely cause harm. And I believe in that. We have to be cautious. However, how to find this trade-off that you then don't stifle innovation? I don't have a great answer for that. However, yes, we have to be in the middle, not be just reckless. However, not be too cautious with please can I get your body points? So yeah, no problem.
There's one question over here. Stand up and state your name as well.
Can anyone hear me?
Yes, I can.
Yeah, I just wanted to ask because in healthcare, if we're making decisions on the basis of data, you
Hang on.
emphasize the importance of data.
Yes.
We just found out that the microphone works better when
I can
it's
hear
switched
you.
on.
I can maybe repeat the question.
Okay. I was just saying that because you emphasize the importance of data, so when we're making decisions or giving recommendations on the basis of less data, how dangerous do you think that is when we're, for example, outlining cases? I mean, maybe with Parkinson's you can find those patterns more easily, but what about in cases where we don't have those kind of same recognizable patterns? For example, mental health issues or anything else like that.
Of course.
What's the danger with making recommendations on the basis of less data?
It's very dangerous, and well, we have a very accurate experimental models, but they're not in the doctor's office yet, because you have to go through the regulations, and they have to be tested, and so that is the reason, because their stakes are very high, and people could die if the algorithm is incorrect. And regarding the data quality, so there's an issue that we are discussing in some communities with doctors. So we have a very high digital society like infrastructure in Estonia. However, there's a gap. Doctors need a very friendly, how do you say, user-friendly operations, right? They just put in and forget it. They don't have to put codes into Excel cells, and no, this is not for them to do. However, for machine learning, you need these Excels very precisely, because you can make wrong predictions based on the unrelevant data. For example, a doctor brought me an example that they take blood pressure, right? And they just put the numbers in, because they want it to be user-friendly, right? They just put the numbers in and they forget it. However, it's a very different thing for blood pressure if it's taken from if you're laying or you're sitting, or is it where is it, or is it from here or from here, or I'm not sure how many choices are there, but it's different how was taken. And if I take this data, I'm very happy, because I have new project, right, to work on. I will map the relations among the high blood pressure. The model will be probably trash, because it won't take these categories into account. However, how to bridge that gap to provide user-friendly systems to doctors. However, on the backside, it inputs all the relevant information for different diseases. Perhaps making some default choices, and well, we need to talk to the government. They need to put systems in place so the machine learning scientists and doctors are happy, and because we have a lot of data, right? They input a lot of data on a daily basis, but how to structure it in that way that the models are accurate.
I also have a question that have you is the microphone working? Okay. We're always talking about how these machine learning algorithms or AI algorithms, they get things wrong. But we usually don't talk about that much when people get things wrong. And when you weigh the alternatives, you know, if you take an average driver, especially, okay, I'm not getting in that territory, but if you take an average driver, it doesn't matter which country, right? And you just take any AI-based self-driving algorithm. Is it Tesla or Mercedes, or who have pretty high autonomy already? And if you look at it statistically, it's very, very likely that the machine outperforms the human, statistically.
Yes, yes, it is.
But somehow we are still not happy with it.
Because of uncertainty, because we can't predict sometimes what it might have. But I agree with you that autonomous vehicles are much more accurate than humans, but the uncertainty part that they can just hallucinate some tracks that weren't there. And
But another question, if you have a choice between going to a family doctor or consulting this even ChatGPT about a medical condition. So what is the average human percentage that an average graduate gets out of that test?
Sorry, that gets...
You had this medical test. It's a final exam or something.
Yes.
Or a medical exam in order to get your papers in order, right? Yeah. So we always see that this machine scored that one much and so on. But how much did the humans score?
Yes.
And more importantly, does it really matter when it comes to diagnosing real people?
Yeah, the one comment on that, so there has been studies that show that even on empathy size, machines are winning. So they're even more empathetical, they have more patience, and whenever patients in terms of, yes, I understand, and when a patient is dealing with a problem, the computers somehow even provide more empathy and are more understanding. So we're even losing on that point, but definitely, yeah, there are some trade-offs that we need to balance.
Okay, we can take one last question. Let's come in there.
Thank you for the presentation.
Yes.
I'm actually interested more into not the large language models, but in the large action models, because I think they're closer to us. I mean, with LLMs, okay, yeah, you get an input, an answer, and then there is a human interaction, right? So you need to read it, you need to trust it, and then use this data, basically. But what about the large action models? I think for us, they're a bit more, let's say, the ones that they will take our jobs, let's say. What's your opinion on this?
Actually, I have no opinion on large action models. I haven't tested them and used them, but if it's something related to agents or something like that, so we have to, well, there are some talks that we have to teach LLMs and have to kind of have a human in the loop, and the human part can be automated with agents, right? So we give feedback to LLMs like, please correct this, please do better, please that, but this can be automated with agents. So it will get better. It will get better. We will mitigate these errors. However, we just have to be cautious and acknowledge that they're not perfect. But yeah, I will definitely look into the LAM. Or
LAM, yes.
Okay,
large action models.
We definitely have no shortage of different abbreviations.
Well, thank you so much for the question.
Thank you, Elli.
Thank you.
So there's a little token of gratitude. Maybe it will help with your fitness diet.
Oh.
So thank you again.
Thank you so much.
And a little bit something to put on the wall.
Oh, thank you. So
thank you again.
Thank you very much. Thank you.